Hello and welcome to my design retrospective. Now the core of the CPU is basically complete now, and so I want to just have a brief pause before I move on to the next bits of circuitry and just talk about where I'm at. And so a couple of weeks ago I put up a video asking for questions, so for the most part I'm going to be working through those questions. Now some people took the opportunity to just post thank yous and say a few nice things. So thanks a lot to all of those. I really do appreciate everybody's support. But I'm going to start off with just a little reminder of the structure of the processor, just so when I refer to bits later, everyone's on the same page. Now at the moment I've got the small LCD screen hooked up, but I've got it with a little camera pointing at it so I can control the screen space it takes up. I've got the Fibonacci sequence test code in place, but let's have a talk about the processor. Right, so on the left here we have the register stack. So I've got 4 8-bit general purpose registers. I've got a special purpose register that I call the constant register, but that's just used for handling 8-bit data that's part of an instruction. The 4 general purpose registers are 8 bits, and they can read and write from the main bus, but they can also assert their value onto the buses I call LHS and RHS. The 16-bit registers are over here, and I call those counter address registers. There's 5 of those, and they're all identical. They can increment and decrement, and they can load from a bus I call the transfer bus, assert back to it, or they can push their value out onto the address bus. So the address registers are all 16 bits, giving me a 16-bit address space. Along the bottom here is a register I call the transfer register, and this bridges the 16-bit side and the 8-bit side by having 2 8-bit registers that also present as a 16-bit register. Down the bottom here we've got the memory unit, and that's currently 32K of RAM and 32K ROM that will go in this slot here, but I've got a couple of videos talking about an upgrade to this that I'm currently working on. Here we've got the memory bridge, and that connects the main bus to the memory subsystem. So it basically allows memory to read and write on the main bus so it can be transferred to and from registers. And that's because the memory is not hardwired to the main bus as it is in some simple processor architectures, because I've got a second channel that allows the memory to be accessed by the fetch unit over here at the bottom of the pipeline, so that the fetch unit can read instructions while the main bus is being used for something else. And that's one of the properties that gives this processor just a little bit of extra speed capability. Down the middle between the registers is the bus control. And what that does is that decodes some of the outputs from the pipeline and turns them into control lines that are used by the registers. So for example, the device that's currently asserting onto the main bus comes from pipeline stage 2 as a 4-bit index, and the bus control has a couple of demultiplexer chips that will turn that into individual control lines that are wired into the registers. Over here at the bottom we have the clock. Now that's got 3 modes. It's got break, trace and run. Now break is basically designed for single stepping, so I've got the single step button here. Trace is slow execution, and run is fast execution from the crystal. So here I'm starting the Fibonacci sequence off. You can see it tick over at a fairly reasonable rate, but it's what I call an interactive rate, in that I can look at the actions of the register and get some idea of the flow of what's going on. If I switch it to run, it will just complete virtually instantly for such a small program. Okay, in the top right hand corner here we've got the ALU. That's split into 4 submodules. So on the right is ALU control. And what this is doing is it's turning a 4-bit ALU operation that comes from pipeline stage 1, and it turns that into the individual control lines that drive the rest of the ALU. So you can basically think about this as a 16-byte memory because there's 8 control lines coming out of it. I could just have easily have done that with a ROM chip and taken much less room, but I really like the way this kind of breaks down and demonstrates the actual actions of the ALU operations. And of course the LEDs here on the operations make it a lot easier to decode what the processor's doing at any given point in time when you're single stepping it. So then you've got the two halves of the first stage of the ALU. You've got the left side and the right side, which are shifting and bitwise logic. The shift unit will output a value unchanged, shifted up by 1 bit, shifted down by 1 bit, or it can also output a 0. The logic side has both the left and right inputs into it, and it can perform a logical operation between those. So it can do a bitwise manipulation of its right-hand input or combine it with the left. And what that basically has is 4 bits coming out of the control, which is a 4-bit lookup. So I can basically reproduce any bitwise operation here, or it can also output a 0 or just like an inverted form of the right-hand input. So the ALU result is the final operation, and what it does is it's an adder. It adds together the outputs from the two early stages, but it also has these 5 flags which it derives from the operation of the data and also uses to manipulate what's going on. So a couple of the output bits from the ALU control determine where the carry flag is coming from used in the add, but also there's some derived flags here such as the sign, 0, overflow, and there's a logical carry that comes from the shift unit. So finally for the modules we've got the pipeline. It's a 3-stage pipeline. At the bottom here is we've got the fetch unit, and that does very little actually. It's mostly just taking what's on the memory data bus and dispatching it into the bottom of the pipeline, and its primary logic here is just to determine if it's able to do that or whether or not something else is accessing memory. But it's got a small piece of logic here where it can hold an instruction back for 1 cycle because there was otherwise a clash that would stop it from working right. Pipeline stage 1 and pipeline stage 2 are where the real work of the processor happens. So they're basically machines that are toggling all of the control lines in the ALU and in bus control in order to make things happen. But if we step the processor, we can see instructions progress up the pipeline, firing the different control lines, activating the ALU, and generally just making things happen. Okay, so I've made a few mentions to buses here, but I think it's worth me going over the specifics of the buses that exist. And I'm going to point out roughly where they exist on the back planes of the processor as well. Firstly, you've got the main bus. Now this is the primary data channel for moving data around the processor, and the wires for that exist in a vertical column down here, and these LEDs tell us what's currently on the main bus. Then you've got the buses that I call LHS and RHS. Now they just extend down this far, and this is any of the 4 general purpose registers can push their value onto either of those buses, and those 2 sides are the 2 inputs over here to the ALU. So the ALU operation is kicked off by pipeline stage 1, so it can select any of the ALU operations, and it can select any of these 4 registers for either the left or the right hand side input, and then in the next cycle the result can be written back to any other part of the processor. And then the other 8-bit bus is mem data. Now this comes out of the memory subsystem, it goes to the immediate constant register, and it goes to the bottom of the fetch unit for pipeline stage 0. And that's just the current byte that's either being written to or written from memory. Now I do have a bus display for it here in the memory bridge. So I conveniently have both the main bus and mem data being displayed in the memory bridge here. And then you've got 2 LEDs here which will give you a signal to show if the memory bridge is pulling data from mem data onto and inserting it onto main bus, or if it's taking the data from main bus and pushing it onto mem data, which is the reverse operation, which is what's going on when the processor is writing to RAM. And over on the left-hand side, we have two 16-bit buses. Firstly, we have the address bus, which is any of the 16-bit registers can push their data out onto the address bus, but only one at a time, obviously. That's controlled by pipeline stage 2 when the address select control outputs. And that's just a one-based indexed into these registers to let them know which one is commanding the address bus. The second 16-bit bus over here is the transfer bus, which is purely used for moving 16-bit quantities around between these registers. So that's controlled by pipeline stage 1, and so any of these registers can be asked to output the data to the transfer bus, and any of the others can load back from it. So the 8-bit registers are general purpose. I call them A, B, C and D. Over here we have the 6 different 16-bit registers, which are PCRA0, PCRA1, the stack pointer, SP, the source index, SI, the destination index, DI, and TX, which is the transfer register. Now, these are called PCRA 0 and 1 because at any given point in time, one is PC, the program counter, and one is RA, which is the return address, but those assigned roles will swap during a function call and a return instruction, so I can perform those operations in a single cycle. That's a simple form of register renaming. Okay, feel free to ask any questions about that stuff down in the comments, but let's get on to the questions that were asked on the invitation a couple of weeks ago. So I've got a different version of me to ask the questions. Let's jump in on those. I had 3 separate questions asking about the amount of current or power that the processor draws. That should be quite easy to answer. That's actually quite a good question. Let's find out. All right, I'm going to remove the Fibonacci sequence ROM because it doesn't actually stress it very far. Let's go with the prime numbers. All right, I've got here a little module for reading USB power. So I should be able to run the build off this USB power bank and get the current draw from this. Right, so we've got kind of a static 0.273 amps while the processor's idling. Okay, so running in trace mode, I'm kind of seeing it spike up to about 0.4 amps. Right, let's run it fast. This is a 1 megahertz crystal in here at the moment. So that's pretty stably moving up to about 0.45 amps. And it's dropped straight back down once it's completed. Alright, I'm going to reset it. Okay, so this dropped down quite a lot when I reset the processor, and the main thing that changed there was all of these address registers reset to 0. So I think that's letting us know that a significant amount of that draw is actually the LEDs. So I might actually write a piece of code at some point which turns on as many LEDs as possible simultaneously, because that might just be the primary thing. There were 3 very high-level general questions about the working of the pipeline. Okay, well, I've already given a little bit of an outline of the pipeline working at the start of this video, but it's not the simplest of subjects, and there is a number of videos already in the series that it really would be worth having a read of. I'm not the best at explaining this stuff in the world, but those videos are pretty much doing the best I can do. But when I speak to people in person, I do find that some people just kind of miss the underlying point of the pipeline execution. So I have come up with a way of explaining that, which I kind of worry sounds condescending to more technically minded people. But I'm going to give you that explanation now, just in case some people are blocked on that. I want you to imagine that I need to do a bunch of washing. I've got a washing machine, I've got a tumble dryer, and I've got an ironing board. And each of those takes an hour. And I've got 4 loads of washing. So the equivalent of a stepped processor would be, I have a very simple kind of model in my head of how to do a load of washing. I put the load of washing in the washing machine. When that's done after an hour, I take it out and I put it in the tumble dryer. I wait another hour. When that's done, I then do the ironing and hang stuff up in my wardrobe. So 4 loads of washing, 3 hours for each load. Very simple formula. But the smart people will immediately look at that process and think, well, there's no way I'm going to take 12 hours to do 4 loads of washing. So there's a very obvious optimization for that. First load of washing goes in the washing machine. Nothing else we can do. But when that's complete, we take that load out of the washing machine and we put it in the tumble dryer, but then we take the second load of washing and put that in the washing machine, because the washing machine is a resource which it's not doing us any favours if it's not doing anything. So at this point we've got 2 things happening at once, and then when that completes we take the first load of washing, and that's going to be, we're going to start ironing and putting away that. The second load of washing goes from the washing machine into the tumble dryer, and then we can start the third load of washing, and that can go into the washing machine. And so for a couple of loads, we've got a load in the washing machine, a load in the dryer, and we've got a load being ironed. And so the entire process gets completed a lot quicker. Basically, that's what the pipeline is for. We've got a whole bunch of different things that can be happening in the processor, and the job of the pipeline is to try and make the stuff that can happen simultaneously happen simultaneously. So instructions are broken down into the simplest steps possible. The fetch unit, if the memory system is available, will fetch an instruction every cycle and dispatch it into the bottom of the pipeline. Pipeline stage 1, its job is to start ALU operations and perform 16-bit moves between registers. It also handles decrements of the 16-bit registers. Pipeline stage 2 deals with finishing ALU operations, moving data around on the main bus, and it also performs a couple of secondary options such as handling the swap between the program counter and return address, and it also generates a break signal, which is what will signal the end of a program or a breakpoint, and that just jumps the clock from whatever mode it's in back to break mode. I hope that helps. You're always free to ask whatever questions you want in the comments, and I always try as hard as I can to give you a good answer. Antonio and AIO Inc., they want to know about a possible extra pipeline step. Okay, in my very original design note that I drew early, I had 4 pipeline steps. So I had the fetch unit and 3 operational steps. And when I first started building the pipeline on breadboard, I did have the 3rd operation step. So a few people have been interested as to why that disappeared. And the actual explanation for that is very simple. I didn't need it. And when I first designed the processor, I was kind of thinking, well, there's some combinations of things here which it might be difficult to cram into 2 steps. But we want the pipeline to be as short as possible while achieving the control goals we've got for the processor. Actually extending the pipeline and making it longer is kind of pointless, because that just increases our instruction latency, the time between starting the instruction and having its operation complete. And I really would have preferred to get away from any of the complexities, such as the value in a register being inconsistent for sequential operations. There's a couple of situations where that's actually true, but for the most part I don't have to worry about that. So the simple answer to that is I didn't need the 4th pipeline stage, and I don't really see any value to having it. Now, if I made a more complicated processor with a bunch of extra options we would need additional pipeline stages. So particularly if we wanted to extend the ALU with more complex operations that can't be done in 2 steps, then we would need a deeper pipeline in order to take the result off the end of that longer ALU. Or we'd need to do something more complex with some internal state to pick up the ALU result at a later point. Hope that answers. Okay, so Ben Christ and James Stanley are asking about whether or not the pipeline nature of the CPU got any tangible performance benefit. Simple answer, yes. The pipeline radically changes the performance profile of this compared to a stepped microcoded processor. So the kind of 8-bit generation of processors I've been most comparing to is the Z80 and the 6502. Now you can't 100% compare instructions per cycle. The Z80 roughly takes 4 cycles for each completed instruction. The 6502 is faster than that, but this processor gets very close to completing an instruction every cycle. All of my ALU operations, my 16-bit moves, increments, decrements, they are all single cycle operations, as are all my register moves. The things that take longer than that are anything that accesses memory. And the simple reason for that is I can't fetch an instruction while the memory data bus is being used for something other than the fetch unit. So it's only memory accessing instructions which are able to stall the fetch unit and prevent me from getting every single cycle dispatching a new instruction. So then the high sustained rate of instructions per cycle I then get from having a pretty flexible ALU and 4 registers with the addition of some other registers I can use for working space in the form of TL and TX and my 16-bit registers. So several of the underlying algorithms I've got, such as the multiply and the divide subroutines, every single instruction in those routines avoids memory, and so I can do very close to a maximum throughput. Right here actually you can see I've got 3 instructions in process. If I step this along, we see that's actually a pretty common state to be in. But eventually, here we've hit a point where I've got some NOPs being generated because of memory contention. So this is a memory read operation going on because the membridge is asserting from mem data to the main bus. Both Neil and Rick ask about the possibility of adding interrupts. Okay, a few people have commented on the fact that I don't have interrupts in this processor. And there's a very simple reason why they're not there. And that's because I didn't see it as something I needed to achieve where I wanted to go with this processor build. Now, some people were a little bit disappointed with that, but I have thought out what it would take to add interrupts. But fundamentally, doing them right is it's something you really need to design in from the beginning of a processor build. And so I wanted to end up with a processor that was fairly clear to understand. And that wasn't going to happen if I took the build as it currently exists and then kind of crowbarred extra functionality that didn't want to fit easily. Now, some features I could add quite comfortably and quite easily just by adding a little bit of extra circuitry, but interrupts would kind of touch a lot of different parts of the processor, and I really didn't want to end up with a kind of Frankenstein's monster build, which would be less penetrable, less easy to understand. Now, I can give you a very quick explanation of what is necessary to add interrupts to a build like this, and maybe that will give you an idea of why I made the choice. Now, the crucial thing about interrupts is an interrupt is a signal that comes from outside the processor core that will change the execution point of the processor to a routine that can handle that. And that means that the processor can react very quickly without whatever the running code is needing to know it might need to react to that particular operation. Now, the reason why I say I don't need interrupts is because I'm very used to writing code that has to take account of possible external factors. So I'm a game developer. I've worked on a lot of different bits of hardware, and it's been quite common to work on bits of hardware that either don't have interrupts, or more frequently the underlying hardware supports interrupts, but there's other bits of code that are using those for other purpose, and I have to make my code work without touching those interrupts in user land. Right, how would we add interrupts? Well, firstly, we need something that is going to store the address of the interrupt service routine. Now, I would obviously want to get interrupts working in a way that was kind of pipeline friendly, high performance, didn't require me to structure the way execution happens different. So the way I would do that would be similar to the way I have the PC RA flip-flop going on, and I would add an additional 16-bit register, which is going to be storage for the location of the interrupt service routine, but it will also become the program counter during an interrupt. So when an interrupt is raised, instead of dispatching instructions from the location of the current program counter, it becomes the interrupt program counter, and we pull instructions out from there and start executing them. And if the interrupt routine is very simple, it can just do a linear series of operations. If it's more complex, it would work out how to save off the program counter, set the program counter to the address of a interrupt service routine, and then it could turn the interrupt off and let the processor continue there, and then we'd have a more complicated return at there that would restore the original program counter address. So we'd need an extra register here, but that's not the only change. Over here is where the problem really comes in. Now, the ALU is stateful. It's got the flags, and you need to be able to modify flags in such a way that the state is preserved within an interrupt service routine. So let's say the code being interrupted is running a loop. It decrements a value, uses the ALU to compare the result to 0. But between that and the conditional jump, the interrupt happens. This interrupt service routine is likely to want to do an ALU operation, and that's going to change the value of these flags, and that's all going to go wrong. We return from the interrupt service routine, and suddenly the carry flag is not right, or the 0 flag is not right, or whatever flags we were actually using. And so the flow of the interrupted program is changed. We can't allow that. So what we would need to be able to do is have a method for saving and restoring the flags. And the way you do that is you have an additional register, so the flags aren't used directly. Whenever we change the flags, we latch the value of the flags into that register, and the output of that register is actually going to be what the rest of the processor sees. And then we connect that register to the main bus so we can perform a save and restore on that register contents, either through one of the GPRs or maybe a push F, pop F instruction pair, something like that. And then finally, there's a couple of situations with the pipeline where an instruction not happening immediately behind another instruction would result in different behavior. So we would have to go through each of those circumstances, and we'd either need to solve that directly, or we would need to just outlaw those instruction sequences, which means that there's a couple of places where we wouldn't be quite as efficient. We might have to insert some NOPs in the code to not break the rules, something like that. Okay, but the two big changes is we would need another register over here. We'd need an extra control line into the pipeline in order to define when the interrupt was occurring, we'd need an extra output from the pipeline to reset the latch that was holding the interrupt status active. And we would need to modify the ALU to allow for preservation of its state. Now, none of those changes are rocket science, but one of the crucial things that would have been different if I'd tried to crowbar that in is I would have broken one of my own rules for this processor build. And that's at no point did I want this processor build to not fit into this camera field of view. Now, the ALU was breadboards stacked from bottom to top, and for most of the time all the surrounding space was filled up, and I looked at different ways of handling this on the ALU, and there was no way to do it without involving additional breadboards, and then I would have been into panning around. Adding an extra register over here, it would have increased space, there would have been imbalance here, but maybe I could have come up with something else to fill the gap over here, or maybe I could have fitted these registers into slightly less vertical space, but I did like the matching vertical size here. So that's my reasoning. If I do a future CPU build, I will definitely include interrupts in, because there's clearly a desire from people to see how they work, see an example and implementation. But I have thought about how to make it work here. I'm pretty sure it would happen, but in terms of this processor build, I really didn't want to get distracted, re-architect half of the modules in this CPU and kind of delay completion of the project by months and months. So I hope that's a satisfactory answer, or at least as close to one as you're going to get for now. Rick and Dennis are asking about extra external storage, and Rick goes on to ask about whether or not I'd write a disk operating system. That's an interesting question, and it's one that I have been giving a bit of thought to. Now, I've been doing the last couple of videos on the processor build have been about changing the memory system to be entirely RAM with a capacity to get some code off ROM. And one of the reasons why I'm doing that is to give me more flexibility about where code comes from. I definitely want to build a system where I can transmit code to the build via the serial port, but being able to load code off some kind of storage medium it's a pretty good idea, and something that's definitely grown on me the more I think about it. So yes, I'm going to add some kind of peripheral that would be a source of long-term storage. I'm not going to have a physical floppy drive in here, but yeah, I've not 100% decided, but I've got a pretty good idea what I'm going to do, but I don't want to give it away just yet until I'm sure that's the route I'm going to take. I think that will probably be a short video series that will come along in parallel to the VJN display, just to kind of break things up a little bit while I'm waiting for PCBs to be delivered, etc. So it should be quite interesting when I get to that. Timbo and Harsh are asking about the assembler and toolchain that I've used in the programming of the build. Okay, there's two main bits of code that are associated with this build. I've got a assembler which I've written, and I've got another program called the control build, and that builds the contents of the ROMs in the pipeline. The assembler I've written is designed to be easily retargetable to any kind of simple processor. And so I'm hoping to release the code and the binaries to both of those programs in fairly near future. I've actually sent them to some people who've asked directly, but at the moment they need a little bit of cleaning up. And one of the things in the assembler takes as an input is, rather than having the code hardwired to the architecture of this processor, is it takes a definition file which actually defines all of the instructions and how they get converted into the binary machine code that the processor is actually going to execute. So when I release that, it's going to be a good source of documentation for what the instruction set is and what the individual breakdown of operations is. So at some point I will upload that to somewhere like GitHub, or maybe get a separate website for it and make a release to anyone. If anyone really wants to see it, send me an email. Paula and Minos ask a very tricky question about what I would do differently if I was doing it again. Now that is a very interesting question. Now, I'm not actually unhappy with anything I've done here. I'm actually over the moon that the processor is working as well as it does, and so close to the design I laid down right at the beginning. But I can talk about a few things that played on my mind a little bit, and if not regrets, they are things that it's nice to think about. Now firstly, in the ALU, there's an interesting complexity here in that I have separate arithmetic and logical carry flags. So the logical carry is used in the shifting, so when you shift a bit off the top and onto the bottom of a register, or vice versa, that's where the intermediate bit of data is stored, whereas the arithmetic carry is when you're performing addition and subtraction. Now the reason why I separated those is because the shift unit happens in a different cycle as the addition and subtraction in the result module. There are ways of making those work together. What you basically end up needing is a piece of state that says where the authoritative form of the carry currently is, and then you set that accordingly to where you actually use it. Or you move the shift operation into the same cycle as the ALU result, and then you can directly shed the same flag bit. Now doing that would actually make the interrupts a bit easier, because then you don't have to worry about the preservation of the flag state between two different steps of an ALU operation. So if I was going down that road, I would definitely re-merge those. But the reason why they're separate is because I've got the separate operation for the shift and the addition happen at different steps in the ALU. Now, I really like the elegance of this solution where you've got two operations that happen independently side by side, and then the result of those operations is combined. But the logical simplicity of that has a price, and that price is this slightly more complicated flag system and the extra complexity of performing the state preservation you'd need for the interrupts. So I'm happy with this. I don't regret doing it, but there is a voice in the back of my head that says life would have been easier if I had merged this up. But once again, I could see no way of doing that and fitting it all on the same set of breadboards. It would have added a bunch of extra complexity to the ALU, which particularly during the breadboard phase would have been a lot more difficult to manage and present videos on. Okay, the second thing that I kind of look back on and think, oh, that's an interesting idea, is something I actually noticed when I was reading the specification for the RISC-V instruction set architecture. Now, I've got instructions and direct operations for moving data between the general purpose registers, but RISC-V doesn't have that at all. Instead, if you want to move, say, from one register to another, the encoded operation you do is actually an addition operation where you are adding 0 to a register and storing it in a different location. And it does occur to me that at no point when I'm doing an 8-bit register move am I using the ALU at the same time, because they both handle this stage in the pipeline. And so I could have actually used that model, and that would have saved me one chip from each of the general purpose registers. Now, I would have needed to make sure I've got a preserving operation in the ALU, but I've got at least one state flag that I haven't used, so I reckon I could have probably done that. Now, once again, I don't really regret not doing that, but particularly if you were trying to build a more efficient processor with a lot more general purpose registers, saving that extra chip on the GPRs would actually be quite handy. So particularly anyone thinking about extending some of these ideas, that's definitely worth thinking about. And there's a third thing, which is an incomplete idea. And this occurred to me about halfway through the build. And I kind of thought about trying to do a redesign to incorporate it, but that would have definitely been a really bad idea. But when you're looking at a complex system like this, it's worth thinking in terms of, do I have a resource that isn't used very much? And in this case I do. The transfer bus is the least utilized bus in the processor, and it exists really and truly for one reason and one reason alone. I need to be able to move 16 bits of data into the program counter to perform a jump or a function call, and I need to be able to do it in a single operation. So I needed this extra bus that was 16 bits wide. Now I did have a fault for having that operation done over the address bus, which would have removed that bus completely, but that would have meant that a 16-bit move operation would have taken up the address bus and it would have dropped me an instruction. It's difficult to know exactly what the performance impact would have been, but it would have been an impact. But I did come up with a realization that when I'm doing a 16-bit move, I'm never actually dispatching an ALU operation. And the LHS and the RHS between them form 16 bits of data. So if I actually made it so that the transfer bus and LHS, RHS were using the same lines, then I could take advantage of that in a few other ways. So I could set any of the 16-bit registers for any of the combinations of 8-bit register I wanted to, but I could also, and that would allow me to do away with the need for the transfer register. Now I'd need some custom ALU operations for getting data back out, because if I pushed the 16-bit register onto LHS and RHS, that would mean that I had hardwired side of the ALU it was going into. So I'd basically need ALU ops that were simply give me the first 8 bits from LHS untouched, or give me the RHS bits untouched. But I could do away with the transfer register. I could have a bus which is heavily used. It would be virtually every cycle it would be used for one job or the other. And I would have a bunch of spare control lines from the transfer register that I think would roughly add up to being able to add a couple of extra general purpose registers. So you can see how that idea was actually very attractive. Now I haven't fleshed it out. I haven't counted all the instruction permutations I'd need to do that, and whether or not it makes sense in the grand scheme of things. But I think there's something there. But there's no way I was going to stop the processor halfway through and make that big a change. But it's something in the back of my head for a possible future build to think about. And if anyone else is looking at this stuff and thinking, I want to do something like James's build, but maybe I want to add to it and do something more interesting, keep that in the back of your head. And there's one final thing that I think is worth mentioning as a response to this question, and that's the address registers are all identical. And that was a brilliant decision, because particularly when you're ordering PCBs, you always get multiples. It was nice to be able to design one module and use it multiple times. But all of these address registers are capable of an increment and a decrement and a simultaneous update. The return address and program counter really need the simultaneous update provided by the output latches. The stack pointer is the only thing that really needs the increment and decrement. SI and DI, I have wired in the decrement, but I've not used it very much in code, and if I didn't have it, I probably wouldn't miss it that much. And so there is basically functionality in these registers that I'm not using. I've got the decrements wired up for program counter return address, but I've never used it. I don't think I've currently got instructions in the ISA for even accessing them. So basically, if I had done different registers on the 16-bit side, I could have saved some parts, saved some cost, and saved a few control lines. I think it's right that I didn't do that, because having the kind of the union of functionality, so I've got 5 identical circuits here, I think actually makes the whole thing a little bit easier to understand, and it makes it easier to assemble as well. But worth considering. Okay, that's going to be probably the longest question answer here, so I hope that was worth it. David from Usagi Electric asks what I think about adding floating point capability. Well, I'm not going to be adding hardware floating point operations to the build. I don't even have multiply or divide, but I did do routines that implemented integer multiply and divide in the same way we had to write routines to do that on early 8-bit micros like the Z80 and 6502. Now those routines were actually pretty efficient, and they're actually part of the building blocks you'd need to write floating point operations. So if you were programming in, say, BASIC on Commodore 64 or a Sinclair Spectrum, you'd have realized you do have floating point operations. You can handle real numbers. And they basically had routines that were performing those operations. So I may well at some point actually write floating point subroutines that can do those operations, and I'd hopefully optimize them just as much as I did the integer multiply and divide to make them as quick as possible. In fact, they might be actually a very strong comparison between this processor and other processors for the underlying performance capability. Saltimer asks how I keep myself from staring at the build and contemplating it for hours straight. I don't. Particularly once I got all of the ALU onto PCBs, I found myself watching it for big chunks of time when I should be more productive. I'm really pleased with how this has come together. Probably not that many hours, but yeah, sometimes I fire up some of these programs and I just watch it. It's more than I could have hoped for. Quite frankly, I'm amazed I've got this far. I was half expecting to hit some kind of insurmountable problem that forced me to kind of rethink my ideas, but I haven't. And it works, and I'm really pleased, and sometimes I do just watch it. Jason is making his own 6502-like processor, and he's asking a couple of specific questions about flag handling. Okay, Jason, now I'm hoping I've kind of already answered your flag question. The mechanic I described necessary for interrupts of having the flags actually latched into a separate register when they change, so that then you can actually modify the contents of that register directly if you need to, is basically the answer you're looking for. Now I do have a clear carry operation that is basically just triggering the operations inside the processor necessary to get rid of the arithmetic carry flag. But if you wanted set and reset operations for other stuff, you could introduce hardware that can directly do sets and resets on those latches directly. Now, your second question about excess flags and how I keep that under control, I strongly suspect is actually about control lines, and we've just got a terminology difference there. And you do specifically mention in your comment Benita's SAP1 processor. Now, he's got a very small number of registers, so he has control lines from the control unit directly driving the operation of those registers. So what I'm calling load and assert operations, he has those as outputs from his control ROMs that he stores his microcode in. And if you've tried to do that for a more complicated processor, you would find yourself with a large number of control lines very quickly. And that's where this bus control device comes in. Now what this is doing is it's using the 3 to 8 line decoders in order to turn index values into a much larger number of control lines. So I've got, for the main bus, I've got 16 assert lines and 16 load lines, which are driven by 4 bits each coming out of pipeline stage 2, and I think that's the bit you're missing. Now you've got 3 to 8 line decoders, but you've also got 4 to 16 line decoders if you search around in the 7.4 series chip lists. But I also show how you can combine these up in different ways in order to get whatever decoder set you want. The second path I have is in the ALU, I turn 4 control lines into 8 control lines by using this diode matrix. Or you could use a second tier of ROM there in the same way I described earlier. But that's another way I actually have much more than 32 control lines spread throughout the build, but I've only got 32 control lines coming out of the pipeline stages, 16 in each. Hope that answers your question. Sed is asking about a possible real-time clock. Interesting idea. I don't really have much need for it. I don't think it would be very difficult to build using a off-the-shelf RTC chip. And so it could probably be integrated fairly easily because you're mostly just getting a little piece of data and asserting it onto the bus on demand. So it wouldn't be difficult, unless you were building the RTC from scratch, which is the kind of thing that I have been wanting to do from time to time. But yeah, I'm not going to be doing that. I might look at a way of integrating an off-the-shelf RTC into a piece of circuitry in the future though, so maybe. This is a scary question. Caitlin is asking if I've got any idea how much this build cost me. Yeah, okay. That's a difficult one to answer. And there's probably lots of different answers. Now, I did do a rough add up. Now, the part cost of what you actually see in front of you right now for the components themselves is somewhere around $140 to $150. On top of that, you've got the PCBs. And that's probably about the same again, but I paid a lot more for that because I was designing and building them on a piecemeal basis, and so I paid a lot more on the postage than I would have needed to. You've also got the added complication, of course, that I've replaced several of these boards, and so I've spent a lot more than that on both the components and the boards themselves. And I've had to buy a whole bunch of tools, so I wouldn't want to attempt to build like this without the oscilloscope, and I bought a fairly decent one. There are cheaper ones available that you might get away with. I've got the soldering iron, the hot air gun, bunch of cables. I had to buy the DuPont kits, bunch of breadboards. I don't want to know what the total of what I've spent. In terms of a hobby, it's given me an awful lot of enjoyment for literally a couple of years now. And so if you kind of take the total spend and divide it down for somebody with a salary, it's not an unreasonably expensive hobby. I certainly don't regret it in any way for the financial reasons, but yes, it certainly cost me a lot more than I expected it to, and I wouldn't like to put an overall figure on what I've spent on electronic parts over the last couple of years. Hope that answers your question. Nick Powers would like to see an additional core to the CPU. Interesting question. I'm not going to do that. Adding an extra core, first and foremost, you need to duplicate basically all of this. Have a second lot of it. The interesting thing about multi-core is not the duplication of all the circuitry, which would be very unwieldy. The interesting thing about multi-core processor development, and the programming side of it as well actually, is the various systems you need to drive in order to make the cores work together and not tread on one another's toes. And so that's an interesting thing that it might be interesting to play with at some point in the future, but not with a build this complex or more complex. Maybe if I do something with FPGAs in future, that would be an interesting thing to do, because instead of soldering up a full new set of boards, you're cut and pasting the operation of the processor inside FPGA logic. So that could be quite interesting. But yeah, not on this build. The embedded hobbyist feels I should program a BIOS ROM and build a tape interface and a simple keyboard. I'm not going to build a keyboard because I've got the serial port. And I mean, if you compare the UART to, say, a PS2 type keyboard interface, it's actually a massive amount of commonality. So there's nothing really to learn or demonstrate doing a PS2 keyboard interface, and I can literally just plug a PC with a serial program on and use my keyboard directly, or I could get a serial terminal and plug that in, and I've got a keyboard and I've got a convenient extra piece of output. BIOS ROM tape, I've said there will be some kind of long-term storage. Tape isn't going to be it though, and yeah, having the default program on a ROM chip be some kind of management code that I can talk to remotely or can access the storage system is probably a good idea, and yeah, I will do that. The Face That Stares asks if I would have found an inbuilt stack register useful when writing programs, and he goes on to ask if this could even be done in a pipeline-friendly way with this design. Okay, I'm not 100% sure on your question whether or not you mean add hardware support for a stack, which I've actually got in the build already. I've got a stack pointer, and I can push and pop any of my 8-bit registers as a standard operation. It takes 2 cycles because I can't fetch a new instruction while the memory op is going on, but it's there and it works, and I've made good use of it, and it's kind of actually essential. I really needed those stack operations to be able to write complicated programs. Now, I did think about making a hardware stack instead before I really started the build and while I was still kind of nailing down the underlying design elements. And that would have been interesting because it would have had an independent RAM chip on there, and a stack pointer that was directly managed by the stack hardware. So you basically, a load and an assert operation would both perform the data move but also handle the increment and decrement of the stack pointer. So that would have freed up a couple of control lines, and it would have also meant that the stack operations didn't take control of the main memory system, so I would have been able to do them back to back and have a slightly increased instruction throughput. But I didn't go down that road in the end because that would have been different from the way the stack works in most standard processors. There is something more like that in some of the microcontrollers that are out there, and that's kind of one of the differentiating factors between general purpose processors and microcontrollers is they can take those kind of liberties and not do the kind of general purpose thing. But there's times in programming where directly accessing the stack via other instructions might be useful to do. So I didn't want to do that. I kept the simplicity, but yes, I've got a hardware stack. People Fighter 189 asks if I'm planning on adding more peripherals in the future. Yes. I've kind of touched on this already, but I'm going to be adding a proper VGA output, and I'm going to be adding some kind of long-term storage. Chuck asks if I'd consider putting my extra boards up for sale after I complete the design. Interesting question. I don't really want to get into kind of reselling of PCBs, but there is this whole kind of thing where many of the PCBs here I just need one of, but you end up getting kind of 5 at minimum. So there might be some value, particularly in the more expensive PCBs, in kind of organising some group purchasing. So kind of let me know if you're interested in that. And particularly, I mean, there are some PCBs here, like the big back planes, which are pretty expensive. And if somebody convinced me that they were actually trying to rebuild exactly this, I might be willing to just send one of the spares I've got over, just to save you that expense. Peter is wondering what clock speed it can reliably run at now it's entirely on PCB. Oh, that's a good question. I don't know. At the moment, I've got a 2 megahertz crystal in there, divided by 2, it's a 1 megahertz clock rate. Now this was predominantly just something I stuck with. I've got a 5 megahertz crystal that I was running divided by 2 for 2.5 megahertz, which was the highest I've demonstrated it running at. But I can tell you that quite recently I put a higher value crystal in there and specifically tested to see if it was stable at 3.146875 megahertz. And it was. And I was very pleased with that because it gives me a possibility for something that I will be doing soon that's quite fun. So if you can take that number and guess the significance of it, and it's got nothing to do with the fact that the first 3 digits match pi, then there will be a bit of kudos for anyone who susses that out. But I definitely want to test out the upper limit. I have mentioned in one of the MakerCast videos that I think there is an issue in bus control which might be capping me out. The new memory module I've got coming will improve my maximum speed slightly, and before I do a final speed test I would like to get rid of the bodges, particularly the one in the ALU, and the clock as well actually. I don't think they'll affect the upper limit, but there will be a future video where I really try this out, and I kind of want to have the display done before then, because at the moment every method I've got for outputting from the CPU is speed limited by something else. The UART is limited by the baud rate set on the device. The LCD, many of the operations triggered the busy flag, which is why we extended that circuit. And so at the moment, if I go from 1 megahertz to 2.5 megahertz, the wait loops in the code just end up waiting for longer. The math operations happen quicker, but the programs only complete marginally quicker. But once I've got the VGA display, I will be able to write programs where an increase in the clock rate is a direct increase in the speed of what you're seeing on the display, and that's going to be way more interesting to do that test then. So look forward to it. Lawrence asks how difficult and how useful it would be to extend the instruction set to support 2-byte instructions. He also asks about memory mapped I/O. That's a good question. I kind of have some 2-byte instructions already because the immediate loads have both the core opcode and the immediate data in the instruction stream as 2 bytes total. But that's not what you mean. You're talking about having more than 8 bits in the actual identification for the operation. And that would certainly be interesting. I'm happy I didn't do that because I obviously rely on the fact that I've got an 8-bit data path from memory, and if I were to have a multi-byte instruction, that would be stalling the fetch unit to pull the extra byte of data in, and so it would drop my overall instruction throughput. And so I'd also have this whole extra complexity in the circuitry, which would make it more difficult to explain the working. And as I've already demonstrated, this is actually a very powerful processor already without having any of that. But it would be nice to have the extra bits, because I could have more registers. And the number of instruction permutations is really the cap on my register count here, and it would have been really useful to have kind of maybe 8 registers. It would also be nice to have separate destination selection for the ALU operations, and the main thing that stops me from doing that is not an architectural restriction of the processor in any way, shape or form. It's just the number of instruction permutations I can fit into 8 bits. So in the future, I may well consider doing a build with a wider memory data bus, and so it'll be a lot easier to do some functionality like that. Might even be possible to have a mem data that's wider than a single instruction, and so we can potentially get away from that bottleneck where a memory operation is a guaranteed stall in the fetch unit. Polygorg asks about caching and RAM. Okay. I don't currently have any caching in the build at all. The RAM architecture is fairly straightforward. I have a 16-bit address and an 8-bit piece of data that I can read or write to that address. And anything more complex than that was kind of unnecessary, but particularly if I wanted to kind of break that relationship between every single memory operation suddenly becomes a 2-cycle op, because I can't fetch while that instruction is executing, then having some caching or some separation like the Harvard architecture would have been interesting, but I really didn't want to go down that road, because straight Harvard architecture introduces restrictions on the processor, because suddenly you can't treat code memory and working memory as the same thing. The modified Harvard architecture, which is what you see in most modern processors, where you have separate code and data caches but driven by the same backing memory, is brilliant. And that's that would be a big implementation though, and in a kind of component-wise circuit like this, you would spend so many chips trying to implement that it really wouldn't be productive. But if I ever do anything with kind of like FPGAs or anything like that in future, I would be very interested in exploring that. Hope that answers your question. I've got a double question from Joel. He asks what my thoughts are on my soldering ability from the start to now. He also goes on to ask if I'm going to make a VGA video card like Benita's worst video card in the world. Well, my soldering's definitely got better from the start, particularly when I was doing all the hand soldering right at the beginning. I made a lot of mistakes, which I tend not to make now. Even very simple things like putting on components the wrong way around it's just kind of a habit forming you need to get to actually check the right things at the right time. More recently, I've been doing the kind of hot air stuff with the stencil to apply solder paste, and that produces much cleaner, much nicer results. But if I look closely, it's very obvious to me which areas of the board I had to touch back up, because the hand soldering just doesn't produce as good results as that. So yeah, that moved forward quite nicely. But yes, I will be doing VGA. I've mentioned it a few times before, but you obviously didn't quite get that. I can show you this. It's a nice, cute little VGA monitor that I'll be using. And actually, my big goal for the VGA circuit is to kind of fit it into the space underneath the VGA display, but in the same general height as the rest of the build, because that will kind of fit the board quite nicely. Now, since you bring up Benita's VGA display, I would say I'm not going to be just copying him. I've been planning the VGA from the very beginning of this build. In fact, I showed the 25.175 megahertz crystal in one of my very early mailbags. just to kind of drop a hint that that's where I was going to go. But what I plan to do is going to be quite a bit more than I've seen people do as a kind of breadboard simple circuit VGA. But I will talk a lot more about that when I actually get to the start of that video series. I'm not going to try and pronounce this, but QUXXY is attempting to make an emulator from the information I've got in the videos. And he's asking if there will be documentation that would support that. Writing an emulator is kind of an impressive goal. I've thought about it myself, although I've not made a start. But yes, I can definitely provide some assistance if you want the data on that. Now the thing you really need is the assembler and the control build code that I've been using to create the ROMs in the processor build. Because if you were doing this from a simulation perspective, I would use the ROMs data verbatim in order to get those interpretations of the instructions correct. And then what you're really emulating is the ALU and the register operations, and that would make it quite flexible to update as well. So at some point in the future I'll be releasing all of that, or if you email me I might be able to get some of it to you sooner. Mechafinch is asking for a detailed breakdown of what the instruction set architecture looks like. Okay, I think I've shown all the instructions in various videos, but it is all very spread out. But the actual full list of instructions is sat there in the architecture file in the assembler. So when I release that, you'll be able to browse through and look at it completely. It would take me a while to talk through all of the instructions, but you've basically got flow control instructions, you've got register move instructions and ALU operations. So I will create a little card and stick it on screen here showing all of my instructions, but it's probably, if you really want to understand what's going on with those, it would be worth just watching through the series and watching out for them. Kyle asks about extending the instruction set, and he also goes on to ask if I'll be publishing an architecture specification. I will be adding just a couple of extra instructions, but I've kind of got to find some space to make room for them. I'm not going to be doing any substantial changes to the instruction set as it currently stands, but at some point I will reorder them all in order to properly group instructions into categories. Because I think that's worth doing at the end, just to keep everything nice and neat. Now, what you actually want in terms of architecture data, the underlying stuff that you don't see in the circuitry is present in the control build and the assembler. In the circuitry, the schematics for the PCBs I've been gradually releasing in my EasyEDA profile. If you check the description, I'll provide a link to my EasyEDA, but go follow me on there, and if you're interested in a circuit that I haven't released yet, maybe prod me and I'll get round to releasing it. I tend to only like to release circuits once I've tested them at least fairly stable and operational, because I don't want anyone to have the expense of a circuit that definitely doesn't work. Okay, well, I hope you found all of this interesting. Now, obviously with the number of questions I had, it's not been possible within a rational time to go into a massive amount of depth for every question. But if you ask questions in the comments here, or go back to videos where I talked about stuff, I do still answer questions on old videos. I don't think there's been any direct question at any point that I haven't answered. So one day I might get so many comments I can't do that anymore, but I don't see that happening anytime soon. So always happy to talk about what I've been doing and what I plan to do in the future. So hope you found this interesting. I'm really pleased with this. I've got a couple of extra videos and then I'm starting on the VGA display, and I'm hoping that all of this will be complete and I'll have some final demos to show before the end of the year. But I'm not always the best at predicting how long this is going to take, and I might get distracted with lots of programming once I've got the display attached to it. But thanks for coming along, and I'll see you all again soon. Goodbye.